All right, you guys, on the way home when I was riding my bike, I realized I was not thinking when I did this problem. Because if I think about a distiller, well, two things. One is that the way it works is, you have some sort of vessel that contains fluid, on the hot plate. This is supposed to be a hot plate. And what happens is you have essentially a tube that distills the liquid and kind of goes down into another container over here. And this is where, I believe, in the problem, they're asking you to determine the length of the tube. So I was not really thinking because the numbers are wrong. So here's the distiller. We get, this 1 liter, I think it was a liter, 1 liter of water evaporates per 30 minutes. And what we know is that in steady state, we're going to condense the same amount of water over here. Condense. And it condenses on the inside of the tube, not the outside. The inside of the tube, and then it will basically, the distilled water will drop down into here. So if we were to draw a blown up version of this, let's say inside here, what we would see is that we have our tube, and this is kind of a cross section of the tube. And here's the condensed water on the inside. Let's do a different color. The condensed water here, and this, what we have out here is the air at 20 degrees C. And the problem says that it's 99.9, the outside surface of the tubing is at 99.9. So we have 99.9 out here, and the inside, since it's where it's condensing, this is going to be 100 degrees Celsius. This is going to be 99.9 degrees Celsius. I don't know why I was thinking you'd get 20. Anyway, it doesn't matter. But I did not even heed my own warning. Of course, with metals, you're not going to be able to maintain an enormous temperature difference, 20 degrees to 99 degrees from one side to the other, and that's what we were doing in class. Anyway, that's just so ridiculous. So here is the problem. You've got now I'm going to redraw this sideways. Kind of like this, and what we have here is the wall. Well, okay, I've kind of drawn it backwards. So we have 99.9 degrees here, 99.9 degrees C here, and we have 100 degrees C on the inside of the wall, and that is the temperature gradient that we are referring to here. So this is the copper. So Q equals negative K, delta T, delta X equals negative K. Delta T is negative 0.1 degrees C. Delta X is, let's see, the difference, 0.75, 1.2. The difference between these two is 0.45 centimeters. That's the total difference. And as Shelby and I think John pointed out to me, you have to divide that in half to get just one of these guys. So it's 0.225 centimeters. So this delta X is 0.225 centimeters. So let me take this to the next page. Let's see how we're doing here. Let's see. We have Q is negative K, delta T, delta X equals negative K, negative 0.1 degrees C, divided by 0.225 centimeters, equals K, which is 300, no, we don't know K. What is K? Maybe it tells us. I'm going to go back. I need to add this file in here. So, what is K? Here we go. We see in the problem K. Oh, here it is, 388 watts per meter Kelvin. So it's 388 watts per meter Kelvin times 0.1 degrees C is the same as 0.1 Kelvin, and the distance is 225 centimeters, 0.225 centimeters times 100 centimeters in a meter. So what that does for us is, let's see, we get this canceled, we get this canceled. So we should have watts per meter squared. And so what do we have here? Just quickly, 0.1 times 100 is going to be 10. 10 times, so we have 3880 divided by 0.225 watts per meter squared. And that is roughly 3,880 divided by a quarter, or times 4 roughly. I'm just sort of, ballparking this. 38 times 4 is 140. 2 is 7, 14,200. Okay, I'm just, again, ballparking this figure. Watts per meter squared is equal to the Q. So here's our Q. All right, if it's that, you can barely read that, 14,200 watts per meter squared is the Q. And our question is, what is the length? How long must the tube be? So what do we have? We have to dissipate 2257 kilojoules in, we have 1 liter, that is 1 kilogram. That means 1 kilogram is, that means we have 2257 kilojoules to dissipate over 30 minutes. And I think we did that in class, 2257 kilojoules per 30 minutes times a minute is 60 seconds. And we've got kilojoules per second, that is going to be kilowatts. So that is, let's see, 60 times 30 is 1800, 2257 kilowatts is, over this number is about 1.2 kilowatts. I'm just looking at this divided by that, 1.2 now, or 1,200 watts. So we take this 14,200 roughly watts per meter squared. Oh no, I take this number divided by that to get the area, and then I need to incorporate the area of the tube, the surface area. Okay, so we have 1,200 watts divided by 14,200 watts per meter squared should give us the area that we need here. So I'm going to just drop this down. We have 12 over 142. That is about 12 over 142 is about 1/12 is, what is 1/12? It's approximately 0.09 meters squared, and I'm just kind of ballparking this because I'm too lazy to get a calculator out, is equal to pi times d times length. Now the d I'm using is the inner diameter this time, so I know that the length is equal to 0.9 meters squared divided by pi, 3.14, times d, 0.75 centimeters, times 100 centimeters per meter. And I'm going to cross these out, so my units are going to be meters squared, and I get the length is equal to what, times 100, so I'm going to get rid of those zeros and move this way, 9 over 3.14 times 0.75. Again, I do not have a calculator. I know 3.14 is also about the same thing as 22 over 7. So I'm going to go 22 over 7 times 9 times 0.75 is, I'm going to call this 3/4, I'm going to say 15, 7 times 9. I'm going to call that half. I'm going to say length is about 4.5 meters. I'm calling that 1 over 2. Yeah. If I used a calculator, it would give me something else, but this is the ballpark figure that I got, about 4.5 meters. You can see that my calculations are off because I've been doing the math in my head. As you can see, I probably have some gross errors here, but this puts us in the ballpark.